not in cold, rainy Boston, but it is what it is. Thank you for the invitation to speak today. And as Serena kind of pointed out, I'll be talking about young 1 million year old pre-main sequence stars called Tauri stars. And Tauri stars are accreting material from their surrounding protoplanetary disks. And simulations predict that matter accretes via the magnetic spheric field lines and onto the stellar surface. And today I'm going to be zooming in and on this particular area here, on the very surface of the star, which is called the accretion hotspot, and focusing on this part of the accretion process. And I'll be using multi-wavelength observations of one star to show that this accretion hotspot has a density gradient, which confirms theoretical predictions. All right, so I've organized my talk into answering these three questions. So for the first, I'll discuss our coordinated multi-wavelength data set of one Tauri star called GMR for the aficionados that are around. And I'll discuss what we found in the multi-wavelength data. Very quick overview. There are two observed features. The first is a time lag between, so we got UV and optical light curves. There's a time lag between the UV and the optical light curves. And the second is a simultaneous dip that we measure in all of our light curves. And I'll go into the significance of that in a lot more detail. The second question, I'll show you then how we use modeling to conclude that these two observed features are telling us that there is a density gradient in the accretion hotspot on the stellar surface. And then I'll conclude with some follow-up work that we're doing using the HST discretionary, a director's discretionary program called Ulysses through a program, a team called Odysseus, which I'm co-PI of, as Serena mentioned in the introduction. So just telling you a little bit about what we're doing with Odysseus. Okay, so first, a quick background on accretion in these young systems, so we're all on the same page for those that are not experts in this particular area. So we have the young star that's surrounded by a protoplanetary disk that goes out to hundreds of AU. The disk is made up of gas and dust, and somehow, we're not sure how, that material moves inward and accretes onto the star, and some of that material is ejected. So as we move inward, there is a point where the temperature in the disk becomes hot enough for dust to sublimate. That happens at around 1400 Kelvin. And there's a hot dust wall here. And inwards of this, we think that there's just gas that makes it through. And this innermost gas disk is truncated by the stellar magnetic field lines. And these young stars, they have magnetic field strengths of 1 to 2 kilogauss, which should be strong enough to truncate the disk. So then gas is truncated here by the magnetospheric field lines, and the material goes along what we call these accretion flows, it shocks on the surface of the star. And these shocks are illustrated here as these light blue bands. And at the base of this accretion shock, which is not shown here on the very surface of the star, is a hot spot on the stellar surface. And that's what I'll be focusing on for most of this talk. So to go over quickly some observables, so this magnetospheric accretion flow, we can study it by looking at broad emission lines in the UV and optical. And the accretion shock emits very strongly as continuum emission in the UV and some in the optical. And yes, I'll be focusing today on the UV and optical light curves that we obtained from one particular system to help us learn more about the accretion hotspot that's on the surface of the star, which is the footprint of these accretion flows that are depositing material on the stellar surface. All right, so here I'm going to be showing these schematics throughout the talk, and I just want to start off with to just show them all at once, and I will be revisiting them in more detail later on. But here, just a quick overview. So the accretion flow is this structure here. It connects the protoplanetary disk to the star. It funnels the materials along magnetic field lines onto the star. At the base of the accretion flow is what we call the accretion column. And I'll discuss this in more detail later on when I talk about modeling. But this accretion column is where the accretion shock is. And it's very close to the star. It's usually shown as a band on the stellar surface, as it's shown here in yellow. And then at the very bottom of this accretion column is the accretion hotspot on the surface of the star. So you can think of it as the footprint of accretion on the stellar surface. And then this is one we'll be focused on today, the density structure of this accretion hotspot and how we can get more information about it. All right, so the accretion column, which leads to the accretion hotspot on the surface of the star, there have been different scenarios that have been proposed for the structure of these accretion columns. So here on the left, we have one column of a single density. Here we have a accretion column with a density gradient where the density increases towards the center of the star, or multiple accretion columns, each that have their own density, or a single accretion column that has a vertical stratification. So these are the different scenarios that have been proposed for the density structure of the accretion column, which then the accretion hotspot on the surface of the star would inherit that structure. And then here are some predictions from MHD simulations of accretion, particularly from the models of Marina Romanova. And her models predict that the hotspot on the stellar surface should have a density gradient, where the density is increasing towards the center. So starting on the left, here we have one of the MHD simulations. The star is in yellow, magnetic field lines are in red, and the blue contours here are the accretion flow, so showing material accreting onto the star via the magnetic field lines. Omega is the rotation axis of the star, and mu is the magnetic rotation axis. And in the left panel is a side view. The middle panel is a top-down view with the gas in the disk in green. And then the right is the accretion hotspot. So the resulting footprint of this on the stellar surface, where here the highest density region is color-coded in red, where the density is decreasing as you go outwards, with orange, yellow, and green becoming progressively less dense. And here the accretion hotspot is bent around the magnetic pole. All right, so before I get to showing you our data set, first I want to show you just a snippet that there's been a lot of previous work on accretion variability in Tauri stars in the UV and the optical. And these objects are known to be very highly variable. So just a little snippet of what's been done, some work that's been done so far. So on the left here is we have HST spectra from the FUV to the very near infrared. And in gray, I've shaded in the NUV. So this is where most of the accretion emission, the emission from the accretion process, the accretion shock on the stellar surface is observed. And so each of these objects has about 3 or 8 spectra, so taken at different times. And I'm highlighting here that you can see that there's significant differences in the NUV continuum. And all of these differences can be explained entirely by changes in the accretion rate onto the surface of the star. And accretion variability is also seen in the optical. So on the right here are optical data taken over more than a month with a cadence of about 8 minutes for 2 Tauri stars. And these two are representative of 2 classes of light curve morphologies that can be attributed to accretion variability. So objects that have light curves that look like the top one are called stochastic, and they have irregular accretion variability. And on the bottom are light curves for objects called bursters, where they have irregular accretion, but then they have short bursts of accretion. Right, so just to kind of quickly show that there is a lot of work in the field on this before we launch into zooming in and focusing on one object. All right, so what is the object that we decided to focus in on and why? So the object is the Tauri star Giamaraghi, and we chose this object for many reasons. First, it's a transitional disk, which means its disk has a large hole that's devoid of small dust grains. So here are all my observations of Giamaraghi. Here's a model where the hole has a radius of about 20 AU and the residuals between the models and the observations. So whenever we see this kind of double peak structure, that's telling us there's a large cavity in the center of the disk. So we wanted an object that had a large cavity because we didn't want to deal with obscuration from the inner disk, causing variability in the optical light curves in particular. We want to see variability just due to accretion. Also, I should say that this study was from the X-ray to the centimeter. So we were looking for an object that would display emission at all wavelengths, hopefully. And this object, Jemuragi, is known to have a jet in centimeter emission. The black contours are the dust continuum, and the white contours perpendicular to that are the correspond to centimeter jet emission from the system. Now, this system, it's also known to have a significant accretion rate onto the star. Despite this cavity in the dust, there's still significant gas that makes it through. And here are HST spectra. In the infrared here, we have specks, but what I want to draw your attention to here is in the NUV shaded area where I mentioned that's where most of the accretion emission from the excess emission from the accretion shock manifests. We see significant variability. So we wanted to target an object that had known variable NUV emission due to accretion. And then lastly, we picked a low mass star, Tauri star, because there's significant evidence that tells us that accretion occurs in these young stars via the magnetosphere, whereas in the brighter stars, the Herbigs, AEBE stars, which are brighter and therefore easier to observe, there it's not clear if the accretion is happening via the magnetosphere or boundary layer accretion. So we wanted to avoid that and just settle for an object where we think we understand how the accretion is materials landing on the star. All right, so here is an overview of the observations in our multi-wavelength campaign with the observatories and the data obtained on the y-axis and time on the x-axis. So the data set includes Swift X-ray and NUV fluxes, HST NUV spectra, Las Cumbres Observatory, Global Telescope, U prime, G prime, R prime photometry, TESS photometry, Chiron, which is a medium resolution optical spectrograph, and we use it specifically to hone in on the H alpha line, and ALMA observations in the millimeter of CO emission lines, and VLA centimeter emission. And these data were taken, and the different colored boxes correspond to the observations, the time of observations. And these data were taken contemporaneously over roughly a month in December 2019. When possible, the data was taken over once a day. And this was motivated by the rotation period of Jemuragi, which is about 6 days. So we wanted to cover the rotation period. The test data was taken about every 2 minutes, and the LCOGT data was taken about 5 times per night. And for HST, we obtained data roughly once a day for a week. And yeah, any gaps that you see that are longer than that are due to poor weather or just scheduling constraints. All right, so that's the data set that we obtained. And we did this because the wavelengths here cover different parts of the star disk system. So to walk you through that, so the X-ray emission traces a radiation coming from the stellar corona. And we didn't find any significant variability in the X-ray emission. And so I'm not going to discuss it further. Jemuragi, in previous observations, it had shown significant variability, but not in this, of course, this set of coordinated observations. So I'm just not going to talk about that further because it was just roughly constant. Now, there was significant variability in the NUV and optical photometry, and that's tracing the accretion shock, also the stellar photosphere, but I'll show you the differences are mainly due to the changes in the accretion on the accretion process. We'll talk about that in more detail. So the vast majority of my talk is going to focus on the NUV and optical variability. And then H alpha lines. So the H alpha emission is tracing material in the accretion flow. And later on, I'll show you how we use this data to measure this radius at which the innermost gas disk is being truncated by the stellar magnetic field. And I'll explain why we want to do that. With ALMA, we got CO emission lines, which trace the gas tens of AU from the star. And then in the centimeter, we're trying to probe the jet emission. Now, we also don't find significant variability in the ALMA, in the radio emission, the ALMA and the VLA. But later on, I'll fold that back in with how this lack of variability is consistent with our interpretation of what is causing the variability in the NUV and the optical. And as I alluded to earlier, we think that it's due to, we're seeing the density gradient, evidence of the density gradient of the accretion hotspot. Okay, so now focusing on the actual variability that we see in the UV and the optical. So, so what do the coordinated multi-wavelength light curves actually reveal? So the first is a time lag between the peaks of the UV and optical light curves. The second is a dip in the UV and optical light curves. And I'll show you why we think that both of these are evidence of a density gradient in the accretion hotspot on the stellar surface. Okay, so here are the NUV through optical light curves of GMRIGI from top to bottom. That we have Swift NUV, LCOGT U prime, G prime. Then we have TESS, and then we have LCOGT R prime and I prime. And then just a note that the TESS band pass is pretty wide, and it encompasses both the R prime and the I prime band passes. And here the uncertainties are all smaller than the symbols. All right, so just looking at the light curves, you can see that there are daily changes, and I'll help guide your eye a little bit better in a little bit, but those peaks that you see are separated by about 6 days, which is consistent with the 6-day rotation period of the star. And so that's evidence of rotational modulation. So there's something on the surface of the star that's rotating in and out of view. So in this case, I'll show you why we think it's an accretion hotspot. Okay, so here with the red shaded boxes in the for the NUV, U prime, and G prime, I'm highlighting the peaks in the light curves, and these boxes are all separated by 6 days, which is the rotation period of GMRIGI. Okay, so now for the TESS R prime and I prime, I'm also highlighting the peaks in the what I'll just call the optical light curves. And again, these green boxes are separated by the rotation period of the star, 6 days. But what's interesting is that the peaks in the optical light curves are offset by about a day by the peaks in the UV data, the U prime, G prime, and UV data. So there is this clear offset between the shorter wavelength emission and the longer wavelength emission. And this can be explained by density structure in the hotspot. So here we have an accretion hotspot. The red corresponds to the densest part of the densest part of the hotspot. And then as you get further away from the center, the density goes down, and the UV emission is tracing the high density part of the hotspot. And the optical emission is tracing the low density part of the hotspot. And as the star rotates, we see the different density regions of the hotspot as it goes in and out of view. So let me press play, and then you can see how sometimes you don't see the accretion hotspot at all. The densest part, sometimes you do. So it really depends on the density structure of the hotspot and if it's in and out of our, whether or not it's in our line of sight. So we think that these time lags between the UV and optical light curves are the first observational evidence of a density gradient for the hotspot on the stellar surface. And I'll go and I'll show in much more detail comparing to MHD simulations a little bit, but first I just want to give this quick overview. Okay, so you saw that. Okay, and then the second observed feature that we see in the light curves is we see this dip that I'm highlighting here in gray. And this happens in all of the light curves where we have the data, and it occurs December 23rd to 25th. And there's actually another dip, December 21 to 21st, but it was very short and it was only caught in the test data. We actually don't have data taken at the times of this dip. So we just don't have the data necessary to see if it was in all the other wavelength bands. But at least for the second dip, we do see it in all the bands. We did have coverage there. So GMRID, like I said, is a transitional disk. It doesn't have significant dust in the inner disk. So these dips are not due to dust extinction. And what's interesting is that this dip is followed by the disappearance of the peaks in the shorter wavelength emission. And then there are peaks after, well, we don't have test data here, but for the R prime and I prime, the peaks are still there, but they're muted, they're lower. But for the short wavelength emission, the peaks they go away. So we think that this makes sense in the context of our explanation of there being a density structure in the accretion hotspot, because this high density region of the accretion hotspot is expected to be very unstable. So since the UV emission, the short wavelength emission is coming from the high density part of the accretion hotspot, when it disappears, then we're going to see a drop in the short wavelength emission. All right, and then quickly, before going and diving more into the details of comparing this in more detail to the models, I just wanted to quickly mention the radio data that we got with ALMA and VLA, because it was the first time that a protoplanetary disk was observed with such a cadence at these wavelengths. And we didn't get any significant variability, but that is still consistent with our interpretation, because if our interpretation is that the variability is due to an accretion hotspot rotating in and out of view. So it's not that the global accretion rate is changing, it's just that our view of the accretion hotspot is changing. And so if the global accretion rate isn't changing, then we wouldn't expect to see significant changes in the X-ray emission or the FUV luminosity. And so we wouldn't expect to see changes in the millimeter lines or in the jet emission, because the jet emission is correlated with the mass loss rate measured from the jet is correlated with the mass accretion rate. So here, just to quickly overview, here we observe the common CO tracers, 13CO on the top and C18O on the bottom. We show this the line to continuum flux ratios as the data points, and we show the error bars are the uncertainties. The solid lines are the mean values, and the broken lines are the 1 sigma uncertainties. And so you see there's no substantial variability. And then here is the centimeter emission of GMRID. So this is tracing the jet emission, and again, no significant variability. All right, so now moving on to compare a little bit more closely with models. All right, so we said there's two observables, a time lag between the peaks in the optical light curves and the UV light curves. So short wavelength, longer wavelength, UV optical. And both can be explained by a hotspot on the stellar surface that has a density gradient. So I'll show you first how this interpretation is consistent with accretion shock modeling, and then also MHD modeling. I showed a little bit of the MHD modeling. So first, let's talk about the accretion shock modeling and how the accretion shock modeling finds that the UV light curves are dominated by the high density part of the hotspot, and the optical is dominated by the low density component. Okay, so first, an overview of the accretion shock models that we're using here. So on the left is the accretion column, which I showed earlier. And here we're using a model, these are models of Gulbring et al., and showing that there's an accretion. So these models assume that there is a vertical accretion column close to the surface of the star that's constrained by the stellar magnetic field, and it's divided into 3 subregions. So you have the pre-shock, the post-shock, and then the heated photosphere below the shock. And then the top of the accretion column is met by the accretion funnel flow, and the bottom of the accretion column is the footprint on the stellar photosphere, the accretion hotspot. And the accretion shock generates emission in the UV and the optical, but where the emission peaks depends on the density of the material. So on the right, we have some simulated emission from the accretion shock model, where each of these lines corresponds to an accretion column with 0 emission, three different energy fluxes. So the red is the highest density and its peak is more towards the left. So it's peaking at the shorter wavelengths. And the purple has the lowest density and it's peaking towards the right, at the longer wavelengths. Okay, so here is the accretion shock model fit to the 6 HST spectra that we obtained during the week of our campaign. I just wanted to show the actual fits. The next slide, I think, shows this in a way that's a little bit easier to grasp for what we're actually pulling out of the models. But I just want to show you the actual fits where the black lines are the HST data. The best fit model is the red line, the solid red line. And that solid red line, the best fit total model, is composed of adding the template photosphere, which is the blue broken line. So let me focus on this one, this line, that's the stellar photosphere. And then these three broken colored lines are three accretion columns of different energies. And when you add these components up, you get the red solid line. So then from these models, we extract some properties of the accretion column and the hotspot. So we're interested in the total energy flux, the density, and the size of the hotspot. All right, so here, hopefully, this is a little easier to digest how we're actually comparing the fits in the previous slide to the data. So here I'm focusing on the light curves during the week where we got the HST data. So this is zooming in just on that week that we have HST data. On the top is TESS, so the optical light curve. The second panel here is the U prime light curve. And you can see the peaks are offset, right? So the peak is for the blue, the U band is here, and the peak for the optical is over here. Now, the third panel here shows the energy flux, so the total energy flux from the accretion column. And the fourth panel on the bottom breaks that up into the fraction of the energy flux that's coming from the low density region and the high density region, where the low density region is in green triangles and the high density region is in red circles. All right, so what I want you to focus on is comparing what peaks, when are the light curves peaking with the model parameters. So when the U prime peaks, the total energy flux of the accretion column and the contribution from the highest density region, the red circle, that's when those parameters are highest, when the U prime is peaking. So this is showing us that this U prime data, the shorter wavelength data, is tracing the energy coming from the highest density part of the hotspot. All right, so, oops. Oh, sorry about that. I think I had a double duplicate slide there, confused me. So on the right here, so the top two panels are the same as the ones on the left, and I'm just switching the model extracted parameters on the bottom here. So now the third panel here is the size of the hotspot, and this on the bottom is the fraction of the hotspot. That's the low density that is attributed, it's called the low density region, and that's in triangles, green triangles, and then the fraction of that, the size of the hotspot, that's due to the high density region, and that's the red circles. So now what you see is that the optical data, this is peaking when the size of the hotspot peaks, and the size of the hotspot is dominated by the low density region. So this is telling us that the optical data is tracing the emission from the low density part of the hotspot. Along with the periodicity in the light curves that are consistent with the stellar rotation period, so every 6 days we're seeing this. So that points to rotational modulation, and that we're seeing a hotspot with a density gradient as it rotates along with the star.
So how density-wise, how high is the density? Could you give us kind of range?
Yeah. So that's like 30. Let me go here and see if I have the numbers. I don't have the particular numbers for these particular models, but this is, it's about 10 to the 10 to 10 to the 12. Yeah.
Thank you.
All right. No problem. Yeah, feel free to shout out with any questions. I know this is a lot to digest and piece together. All right, so that's the accretion shock modeling, and that's telling us what parts of the light curve are tracing what parts of the accretion hotspot. So now I want to compare the light curves to the MHD simulations of Marina Romanova. And as I alluded to earlier, the MHD simulations predict a time lag in the light curves. And they also predict that the high density light curve peaks can disappear because this region is unstable. Okay, so first let's go through the setup of the simulations. And we use the global 3D MHD simulations of Marina Romanova, particularly the models from Blanova 2016. And these are of a rotating magnetized star that's accreting from a disk. We have the 3D view up there. And then the models, and here we have a side view and a top-down view. And the models assume that the star has a dipole magnetic field. The rotation of the star, again, rotation axis is omega. The magnetic axis is mu. And the angle between the two, which is not shown just for clarity, is theta. And that's often called the misalignment angle. And then here is the accretion hotspot that's generated by these models. That's crescent-shaped, bent around this magnetic pole, and it has a density gradient. So MHD simulations take months to run. So we went through the simulations of Blanova et al. And chose the simulations that had the parameters that are most similar to GMRIG. So the simulations show that the properties of the hotspot depend on theta, so the misalignment angle, and the what's called the magnetospheric truncation radius. So that radius at which the innermost gas disk is cut off by the magnetic field. So essentially the size of the stellar magnetic field. So theta, we got from, so the misalignment angle, we got from this work, McGinnis et al. 2020. So they measured the location of the hotspot of GMRIG. They placed it at a high latitude of about 77 degrees. And they were able to get at the latitude of the hotspot using radial velocity variations of the helium-1 line. And then combining that with the projected rotational velocity V psi I. Yeah, so they predict a misalignment angle of 13 degrees. So we looked for the simulations that had theta is consistent with this. And then for the magnetospheric radius, we are able to measure that using, we have models from Musrol et al. Of the accretion flow onto the star. And we fit the H alpha optical spectra that we took with Chiron. And we measure a size of the magnetospheric radius of about 4 stellar radii. So just to remind you, the accretion flow, so that's this structure here, and we can measure the magnetospheric truncation radius using models of Musrol et al., but here we're following Bodhi et al. And the in black are the Chiron H alpha observations of GMRIG, and the red are the model fits. And from that, we get for our star. All right, so that's how we picked the simulations. And here we have some simulated light curves that are generated by the hotspot in the MHD models, where here it's separating out the light curve you'd see from just the low density region and the light curve you'd get from just the high density region, where the low density region of the hotspot is the solid green line. And again, that's dominating the optical emission. And the high density region of the hotspot is dominating the UV emission, and that leads to the broken line. So both of the light curves are predicted to be modulated by the stellar rotation period. And there is a time lag between the light curves. You can see that more clearly in this peak here in the middle and over here. And that's due to as the high density region of the hotspot rotates into and out of view. So that explains the time lag that we see in the light curves. And the position, the shape, and the structure of the hotspot varies with time. So and the high density part is very unstable. And so it can occasionally disappear. So you see it disappear here in the simulations. And I forgot to mention that this x-axis here is the time measured in units of the stellar rotation period. And at 2p star and 4p star, the peaks from the density part of the accretion hotspot disappear. So that's predicted because it's unstable. All right, and that's consistent with us seeing some of the peaks in the UV emission disappear after we see that big dip in all of the light curves. All right, and then the right panel focuses on one of these peaks, the one around 3p star. And I'm going to step through these in a little bit, but as an overview, we start off here in time, 2.6p star. We're just starting to see the hot spot, and so we're starting to see the emission increase here in the light curves. And then as the hotspot gets into rotates into view, we get peaks in the light curve, and as it rotates out of view, we get a decrease in emission. So here I'll just step through as you see a graphic here show up on the right, you'll see a line show up on the left that corresponds to where it is in this peak here. All right, so now we're seeing more of both the high density and the low density part of the spot. And as a reminder, red here is what's color coded as high density. And then here, green and blue we're getting to the lower densities. And then here we see all but of both, but the smaller, but the high density part is more along our line of sight. So we're approaching the peak. And then I'll just quickly go through here because I think you get the gist. And then here we're seeing the accretion hotspot is starting to get hidden. So we start to see the decrease in the emission and light curve. Okay. All right. So where do we go from here? All right. So I focused a lot on just looking at the accretion hotspot on the stellar surface. But there's also a lot of work that can be done on just accretion in general. And I'll be, in the next few slides quickly, I'll describe what we can do in this area, particularly with Ulysses, which is an HST director's discretionary program. All right, so the HST director approved a discretionary UV legacy program with 1,000 orbits to obtain UV spectra for pre-main sequence stars and high mass stars. And this program was called Ulysses, the Hubble UV Legacy Library of Young Stars as Essential Standards. All right, so this is the largest HST program ever executed at 1,000 orbits, and half of that was for YSOs. And so 500 orbits for YSOs, and of that, 100 orbits were dedicated to monitor 4 targets in particular for variability. And one of these was Geomorrhagi. And 3 of the 4 targets, including Geomorrhagi, were coordinated with tests. The HST observations were coordinated with tests. And the data collection was completed at the end of 2022, and the papers are starting to come out from the community. And I'll just quickly overview some of our first results. So first, a little bit about Odysseus. So the Ulysses program, you can imagine getting a very large resource dedicated to a relatively small field, got us all very excited, accretion aficionados, and we banded together into a team of over 100 scientists around the world, and we call ourselves Odysseus. Outflows and disks around young stars, synergies for the exploration of Ulysses spectra. So going with the HST theme. So our team's goals are to study the accretion flow, to study winds and jets, and the FUV radiation field. And we're an open collaboration. We have virtual meetings about once or twice a month where we talk science, accretion related science. So if you're interested, if you're an accretion aficionado yourself, you can go to our website here, and there's a contact form if you want to join, and you can also email me directly if you want to join in and listen in on our telecons, which are about twice a month. All right, so one of the strengths that comes with having such a large collaboration is that we were able to get a lot of coordinated ground-based data, contemporaneous in time, along with the HST observations. So we have a lot of multi-band light curves, a lot of optical spectra, A lot of it's from NORLab through with Chiron, which I showed earlier, Chiron data, but also there's a large ESO program called Penelope, led by Carlo Manara, which is collected also X-Shooter espresso data, coordinated in time with HST. So a lot of data. So here are our first 4 papers listed here. I'm quickly going to overview the first 2, which are the ones that are focused on accretion work. The others are looking at the FUV. So the accretion work focuses more on the NUV. And this was just the first overview paper from our team, introducing Odysseus and just kind of showcasing all the data we can collect through the team. So on the right are the HST data. Here we have the NUV up to 1 micron. And then, this is NUV through near-infrared with HST. And then this data at the longer wavelength, that's X-Shooter data that was gotten through Penelope. And then the bottom here is FUV. And the top left is just an example of some light curves that we obtained. And here are some high resolution spectra of optical lines. I think this is with espresso. So yeah, just showcasing the data that we got, or that for Odysseus. And like I said, we're still processing a lot of this data. One of the first results that we got out of the team was led by my grad student, Kaylee Pittman. And she found that, and this is just showing the accretion modeling fit to one particular object. I explained kind of like how the broken lines correspond to the photosphere, the accretion shock, and the red line is fitting the data. That's the HST, the black line is the data, the red line is the model. But the point of the paper is not this particular object, but that we're finding that when we're fitting the HST data, we have the NUV, that's where most of the accretion energy is coming out. We're finding that accretion rates are about a factor 4 higher than were previously reported. And this is just looking at like the first dozen or so objects that came out very early. Now that we have all of the objects, we're going through the sample and seeing if this holds up. And if it does, that would be a significant impact on our understandings of accretion rates. So that's something we're still working on. So Kaylee's leading that effort, looking at the rest of the sample and seeing how high is the accretion rate. And then I mentioned that there were 4 targets. We call these the monitoring sample. They had 100 orbits dedicated to them, and they were observed many times to cover 3 rotation periods. I think they were sampled about a couple times per rotation period. Again, just showing you the data. There's a lot of data. We're still in the process of going through most of this data. But this effort is being led by John Wendingvoord, who is another graduate student in my group. And on the right, top right, are the HST NUV spectra. And here's Jim Aregi. And we have also in the sample RY Loopy, TW Hydra, and BP Tau. And you can already see just striking variability in the NUV continuum. Here on the bottom, we have optical spectra with Chiron that we're taking contemporaneously with the HST data. So we still have to dig in there and look for correlations. And on the left are the extensive light curves that were obtained by the Odysseus team. And for each of the objects, TW Hydra, RY Loopy, BP Tau, and GMRID. And the vertical black lines are the times of the HST observations. So again, a lot of data, we're going through it. And so stay tuned for hearing some results from the Odysseus team with our very large data set coming out in the next few months. All right, so to summarize, 2 main takeaways from my talk. So the first is that for 1T Tauri star, using multi-wavelength observations from the UV to the optical, we see variability that is consistent with a hot spot that has a density gradient that's rotating in and out of our view. And these observations confirm the theoretical prediction for the first time that there should be a density gradient in the hot spot on the surface, which then translates to the accretion column having a density gradient and the accretion flow having a density gradient. And it also showcases the importance of having coordinated multi-wavelength observations of these very active systems at multiple wavelengths. And then the second takeaway is that In the near future, there's going to be a lot of progress in the field of accretion onto Tauri stars with the Ulysses data set. So stay tuned. And if you're interested in joining Odysseus, please reach out on our website or by emailing me. So thank you very much.
Thank you. Thank you, Kathleen. So now it's the time for question from, if you have a question from online audience, please raise your hand. And you can ask for, wow, let me ask you first. So I would like to ask you about the X-ray variability, whether if you expect to actually see it, and if the Swift sensitivity was good enough to actually test that. And the second related question is whether the amplitude of variability for X-ray may be smaller, or is it all because of sensitivity?
Yeah, good question. So the Swift data that we got were only measuring the X-ray luminosity. And so most of the accretion energy, the energy from the accretion process gets absorbed by the X-rays get absorbed by the stellar photosphere, we think. And we wouldn't expect to see changes in the X-ray luminosity due with the data we got from the star. We were more looking for the corona, just the stellar activity. For accretion-related X-ray variability, we would have had to get spectra in order to see accretion-sensitive lines, and we did not do that because it would just be a very significant time request for these relatively faint objects. So yeah, we weren't expecting to see variability due to accretion in the X-ray. We were tracing the X-ray to trace just the variability of the corona itself to see if that could be impacting any other part of the disk system. And we saw that the variability in the X-ray was roughly constant. Or I mean, the behavior, there was no very significant variability.
Okay, thank you. Joan?
Hi, Catherine. Thank you so much for the wonderful talk. I had a question about the second part of your talk where you mentioned that you were finding much higher accretion rates than previously. Can you say a little bit more about that? Is that is it that all accretion rates will be enhanced by a factor of 4, or are there other factors that might change the relative accretion rates of things? And what is the change in the accretion rate primarily due to? Thanks.
Yeah. So first, we still have many more objects to go through. This was just for the first dozen, and this was comparing it. It's a factor of 4 higher than the canonical Hartmann average accretion rate of 10 to negative 8 solar masses per year. So you think it could be due to 2 reasons, and we need the larger sample to figure it out. So first, it could be that these most accretion rates are kind of bootstrapped from, there was an original paper that makes some correlations with the NUV and some other correlations, and it's kind of bootstrapping from that. But most accretion rates are not directly measured using NUV data, which is where most of the accretion emission comes out of. So it could just be that now that we're actually we're looking where most of the accretion emission comes out of, these other tracers like H alpha and U-band and things that were kind of extrapolated from that. Maybe we need to revisit those correlations. The second could be maybe it's just the model that we're using. So our model is so we're using the Galbraith and Calvet models, and those are multi-column models. So it could be that I showed that figure where depending on the energy, the emission peaks at different wavelengths. So it could be that since we have the NUV data, perhaps the model is doing, it's fitting all of the emission. I forgot to mention we're fitting the NUV out to the optical because we have the X-shooter data. So it could be that there is emission that hasn't been accounted for before. So it could be like that we're including the NUV. It could also be that we're using a multi-column accretion model that can try to reproduce the emission at all the wavelengths from the NUV to optical. So I would say for that, I'm not going to say all the accretion rates are off by a factor of 4. I'd want to wait and see if there's just something, because the region we did was Ori 1, Sigma Ori, I think it was. And maybe there's just something different about that region or the objects that were picked in the sample. So I'd want to wait until we have the bigger sample to be able to say something robust on that. But preliminary
Thanks.
results show factor of 4 higher.
Great, thank you. Look forward to the rest of the results.
Okay, Alison. Oh, you had a question too?
Yes.
After Alison, yeah.
Thank you very much for a nice talk. I had to step out briefly, so I'm sorry if I missed this. I was wondering what you think the relationship is, or if there's a relationship between these accretion hotspots and known sort of episodic accretion events or accretion burst events. And in particular, you know, are these accretion hotspots, you know, sort of, do they vary in density, but they're kind of always permanently there in that general spot on this photosphere? Or are they, you know, if you looked in archival data, would you expect to see flares in the centimeter, you know, a few years prior for these sources, that sort of thing?
Yeah, that's a really good question. I think, yeah, so like, you know, we went into this thinking that we were going to see accretion, like global changes in accretion variability. So instead, for this particular time that we were looking at GMREGI, all of those changes that we see were rotational. And if we didn't have the data sample, the sampling with the rotation period, maybe some, you know, if we didn't have that, maybe we would have said it's due to global changes in accretion. But we have, since we have the sampling we know it's due to rotation. But in the past, like I mentioned that GMREGI, we picked it because it had NUV variability. In the past, it did have, how can I say? It did have accretion bursts where the accretion rate was higher than we see in our data set in 2019. So I think objects can have two types of variability that we see. So one is just the variability of what are we seeing, the accretion hotspot rotating out of view, and then just an actual change in the amount of material that's being deposited on the surface of the star. So GMREGI has had much higher states of accretion measured than we picked up in this particular data set. But since we didn't have that sampling, we don't have the comparison of, you know, is it rotational or is it on top of the rotational variability? And my student, John, he is looking into that for GMREGI. That is on the list of things to look at to try to distinguish between, did we catch any accretion bursts on top of the rotational changes that we see in GMREGI in particular. And I think that can be extrapolated to other kinds of other Tauri stars as well.
Okay, thank you.
Yeah, go ahead.
Hi, Catherine. This is Jaron Leissenring. Really nice talk. So I just wanted to say it's a really nice data set with the coordinated observations. You know, as you know, it's really, I think it's really key to get a lot of that info simultaneously. And so one of the questions I kind of had relates to JWST MIRI, and if these, if you have any plans to sort of coordinated try to get coordinated observations for mid-IR, you know, because there's so many nice water lines, and you can get dust processing events, and it'd just be really cool.
Yeah, I'm laughing because I have an accepted program. And I maybe I'll regret it because variability is just such a pain. But accepted program Chandra, HST, and JWST for 3 objects. But it's just kind of snapshots. It's not repeated because it is a big time request. I did try in cycle 1 to do something for GMREGI. The TAC didn't like it. We weren't successful. Maybe in the future, as more of these more information gets out with Odysseus, maybe we can put together a more convincing story. But initially for cycle 1, the TAC was resistant to repeated observations of one object, understandably, because you know you're kind of in a way you could be fishing if you don't know exactly what you're looking for. But for cycle 2, we did get 3 observatories, X-ray, UV, mid-infrared, looking at 3 objects one time. So kind of a snapshot in time. So we won't be able to follow changes, but we will be able to try to tie together the emission that we see at the high energy with things that we see in the mid infrared.
Awesome. Yeah, so that might be a great pilot program for something more going forward. Yeah, I worry that because MIRI MRS kind of has had some hardware issues over the past year, and it gives me concern about its future.
Yeah, it is disappointing that, right? Like our favorite instrument for many of us is the one that's having issues. But yeah, I share your concerns and kind of this kind of urgency to get our disk data early.
Yep. Okay. Any other question? Yes.
Yes, I have a question about is that the hotspots associated with the created by this completed shock. For this in young stars, it could have some cold dark spot on the surface. And I'm wondering, did you ever consider these dark spots in your modeling? And how is the effect on this significant?
So I got pieces of that. I think the question was something like cold spots,
Yes.
dark spots, and if we consider that. So we don't see evidence for the dark spots, any dark spots on GMRE. There are on so some T-Tauri stars that are not accreting, weak T-Tauri stars. Some of them do have these evidence of having these cold spots on the surface. To the best of my knowledge, GMRE hasn't had any reported to date. And we don't see any evidence of it in our data set. But the weak T-Tauri stars are known to have these dark spots.
Maybe it's hard to detect that with the accretion actually.
Yeah, the accretion would just like outshine it.
Right.
Yeah.
Right. Okay, any other question? Yes, sure.
Very nice talk. What is the time scale of a hotspot on the surface of the star? Is it like one accretion event creates a hotspot that lasts for some one amount of time, or is it continuous gas inflow that creates this hotspot that lasts like very long time?
Yeah, that's a good question. So according to the MHD simulations, it depends on what regime you're in. So if you're in the stable regime, the accretion hotspot is relatively stable, it stays there for a long time. I forget off the top of my head how many rotations it's predicted to stay there. But if you're in the unstable regime, the hotspot is expected to, depending on the structure of the accretion flow, to be very unstable, the accretion hotspot. And then, we talked about how the high density part itself is very unstable, but this is for the larger accretion hotspot itself. So it depends on whether you're in the stable or unstable regime, and then GMRE is right on the border between the stable and unstable regime. Yeah.
Okay, I have a lot of questions, but I will follow with you separately. So do you have any other question from online audience? Nope, here. Okay, let's thank Kathleen again.
Thank you.
And